Welcome to this coding problem walkthrough. Today, we'll be tackling problem number 1893, check if all the integers in a range are covered. In this problem, we'll explore how to verify whether a given range of integers is fully covered by a list of subranges. Let's dive in and break it down step by step. The problem asks us to determine if all integers within a specified range are fully covered by a set of intervals. We are given a 2D array called ranges, where each element represents an interval in the form start_i, end_i. Additionally, two integers, left and right, define the range we need to check. The task is to return true if every integer in the inclusive range, left, right, is covered by at least one of the intervals in ranges. Otherwise, we return false. For an integer to be considered covered, it must satisfy the condition where it lies between start and end of at least one interval, inclusive. The input format specifies the constraints for the ranges array, as well as the values of left and right, all of which fall within the range of 1 to 50. The output is a Boolean value, true or false, based on whether the entire range, left, right, is covered. To understand the problem better, let's look at an example. Suppose we are given the intervals 1, 2, 3, 4, 5, 6, and the range to check is left, right, equals 2, 5. The task is to verify if all integers from 2 to 5, inclusive, are covered by these intervals. Breaking it down, the integers in 2, 5 are 2, 3, 4, 5. Now, 2 is covered by the interval 1, 2, 3, and 4 are covered by the interval 3, 4, and 5 is covered by the interval 5, 6. Since all integers in the range 2, 5 are accounted for, the output is true. Now consider a different example. Here, the intervals are 1, 10, 10, 20, and the range to check is left, right, equals 21, 21. In this case, the range includes only the single integer 21. To determine if the range is covered, we need to check if 21 falls within any of the given intervals. However, the intervals provided only cover integers from 1 to 20, so 21 is not covered by any of them. As a result, the output is false. In another example, we are given a single interval 1, 50, and a range to check of left, right, equals 1, 50. Here, the interval spans all integers from 1 to 50, which perfectly matches the range we need to verify. Since the entire range, 1, 50, is fully covered by the interval 1, 50, the output is true. This illustrates that if a single interval fully encompasses the range, the solution is straightforward. It's important to note that the intervals in ranges can overlap, and this is perfectly acceptable. Overlapping intervals may collectively cover the range we are checking. For instance, if multiple intervals each cover parts of the range, left, right, they can work together to ensure that the entire range is covered. The key is to evaluate all intervals and confirm whether every integer in the specified range is accounted for by at least one interval, regardless of overlaps. To start, the brute force approach is the most intuitive way to tackle this problem. Here, we iterate through every integer in the range, left, right, and check if it is covered by at least one of the ranges provided in the input array. For each integer, we examine all the ranges and verify whether the integer lies within any of them. This is done by confirming if the condition start_i equals x equals end_i holds true for at least one range, start_i, end_i, in the list. While this method is conceptually straightforward and easy to implement, it involves nested loops, one for the integers in the target range and another for checking all the input ranges. As a result, the time complexity is proportional to both the size of the target range and the number of input ranges. This can become computationally expensive for larger inputs. However, it's worth noting that this approach does not require any additional memory, making its space complexity constant. Now, to improve the efficiency, we can use an optimized approach based on the prefix sum technique. The idea here is to utilize a difference array to track the effect of the ranges on the coverage of integers. Instead of checking each integer against all ranges, we mark the start and end points of each range in the difference array, incrementing at the start index and decrementing just beyond the end index. After processing all the ranges, we compute the prefix sum of the array to determine the total coverage for each integer. In practice, this means creating a difference array that is slightly larger than the maximum possible value of right, for example, 52 based on the problem's constraints. For each range, start_i, end_i, we update the difference array by incrementing at start_i and decrementing at end_i plus 1. Once all ranges are processed, the prefix sum of this array tells us the coverage at each position. Finally, we can verify whether all integers in, left, right, are covered by checking if the prefix sum is greater than 0 for each of these integers. This approach is significantly more efficient, with a time complexity proportional to the sum of the number of ranges and the size of the difference array, and a space complexity determined by the size of the difference array. Alternatively, we could use a sorting-based approach combined with binary search. Here, we would first sort the input ranges by their start values. Then, for each integer in the target range, left, right, we use binary search to determine whether it falls within any of the sorted ranges. While this method avoids the nested loops of the brute force approach, it introduces the overhead of sorting the ranges and performing multiple binary searches. This makes it less efficient overall compared to the prefix sum technique. Specifically, the sorting step alone adds a cost proportional to n log n, where n is the number of ranges, while the subsequent binary searches introduce additional complexity proportional to the size of the target range multiplied by the logarithm of the number of ranges. Although this method is a feasible alternative, it is neither as intuitive nor as computationally efficient as the prefix sum approach, especially for larger inputs. After evaluating the different approaches, we chose the prefix sum technique as the most efficient and clear solution. Unlike the brute force method, which becomes computationally expensive for larger ranges, the prefix sum approach processes the ranges in a single pass to mark coverage and verifies it in another pass, making it both time and space efficient. Additionally, it avoids the sorting and searching overhead required by the binary search approach. The key insight here is that this problem can be reduced to a range update and query problem, which the prefix sum technique handles optimally. While the brute force approach is simpler to understand, it's impractical for larger inputs. The sorting approach, on the other hand, is more complex and less efficient than the prefix sum method. By balancing simplicity with efficiency, the prefix sum technique emerges as the optimal choice. This strategy not only ensures clarity in implementation but also achieves the best possible performance given the problem constraints. In this problem, we are tasked with determining whether every integer within a given interval, defined as left, right, is covered by at least one range from a set of ranges. Each range is represented as start, end, meaning it includes all integers from start to end, inclusive. For example, if one of the ranges is 3, 5, it covers the numbers 3, 4, and 5. The input consists of an array of ranges and the two integers, left and right, defining the interval. The goal is to return true if every integer in the interval, left, right, is covered by at least one range. If even one integer in this interval is uncovered, we return false. This sets the stage for developing a systematic approach to solving the problem efficiently. To solve this, we first need to understand the problem deeply. Imagine we are given the ranges 1, 4, 6, 8, and the interval 2, 7. Here, the integers 2, 3, and 4 are covered by the range 1, 4, while 6 and 7 are covered by the range 6, 8. Since all integers in the interval 2, 7 are included in at least one of these ranges, the result would be true. Now, the simplest way to approach this is through a brute force method. The intuition is straightforward: iterate through each integer in the interval, left, right, and for each integer, check if it falls within any of the given ranges. If you find even one integer in, left, right, that is not covered by any range, you return false. Otherwise, if all integers are covered, you return true. While this approach is conceptually simple, we will later explore ways to make it more efficient. To implement the brute force solution, we can break it into clear steps. First, initialize a loop to iterate through all integers from left to right. For each integer x in this loop, iterate through all the ranges provided in the input. For each range, start to end, check whether x falls within this range by verifying if start equals x equals end. If the integer x is not covered by any range, you immediately return false. On the other hand, if you complete the loop without finding any uncovered integers, you return true. However, this approach can become inefficient when the interval, left, right, is large or there are many ranges to check. To optimize this, we can leverage a coverage array to pre-process the ranges and reduce the repeated checks. The optimized approach involves using a coverage array to efficiently track which integers are covered. First, initialize a Boolean array called covered, with a size equal to the maximum possible integer in the ranges plus 1. Each index in this array represents whether the corresponding integer is covered. Next, iterate through each range in the input. For each range, start to end, mark all indices from start to end in the coverage array as true, indicating that these integers are covered. Once the coverage array is populated, verifying the interval, left, right, becomes simple. Iterate through all integers in, left, right, and check if the corresponding value in the coverage array is true. If you find any integer that is not covered, return false. If all are covered, return true. This method significantly reduces the computational overhead compared to the brute force approach. This optimized approach provides key insights into efficiency improvement. The brute force method has a time complexity of O, right, left, asterisk n, where n is the number of ranges, because for each integer in, left, right, we check all ranges. In contrast, the optimized approach reduces this to O, and plus max, where max is the largest integer in the ranges. This is achieved by pre-processing the ranges into a coverage array, which allows for constant time checks during the verification step. Additionally, there are specific edge cases to consider. If the input ranges are empty, the result is false unless the interval, left, right, is invalid, such as when left is greater than right. If left, right contains only one integer, you simply check if that single number is covered. Overlapping ranges are also handled seamlessly by the coverage array, as marking an integer as true multiple times has no adverse effect. The data structures used in this solution are straightforward yet effective. The main component is the Boolean coverage array, which is used to mark and verify which integers are covered. The size of this array depends on the maximum integer value in the input ranges. Additionally, loop variables are utilized to iterate through the ranges and the interval, left, right. When analyzing the complexity, the time complexity of pre-processing the ranges into the coverage array is O, n, where n is the number of ranges. Verifying the integers in the interval, left, right, takes O, right, left. Therefore, the total time complexity is O, n plus max. The space complexity is dominated by the coverage array, which is O, max. This balance between time and space efficiency makes the optimized approach highly practical for this problem. To solidify our understanding, let's walk through an example. Given the ranges 1, 4, 6, 8, and the interval 2, 7, we first initialize the coverage array. Next, we mark the integers 1 to 4 as true based on the first range and mark 6 to 8 as true for the second range. Now, we verify the interval 2, 7. The integers 2, 3, and 4 are marked as true from the first range, and 6 and 7 are marked as true from the second range. Since all integers in the interval are covered, we return true. This example demonstrates how the optimized algorithm efficiently checks coverage using the pre-processed coverage array. This implementation solves the problem of checking whether all integers in the range, left, right, are covered by a set of ranges. Let's break it down step by step. 1. Input preparation. The algorithm begins by defining a coverage array of size 51, since the problem guarantees that ranges are between 1 and 50. Each index in this array corresponds to an integer, and its value will indicate whether this integer is covered by any range. 2. Marking coverage. Using a loop, we iterate over each range in ranges. For each range, start to end, we mark the positions in the coverage array as 1 for all indices between start and end, inclusive. This ensures that all numbers within any given range are marked as covered. 3. Checking the target range. Next, we check each number in the target range, left, right. If any number in this range is not marked as 1 in the coverage array, it means that number is not covered by any range, and the function returns false. 4. Return true. If the loop completes without finding an uncovered number, the function returns true, indicating that all numbers in the target range are covered. #### edge cases. If ranges is empty, the function will return false because no numbers can be covered. If left and right are the same, the function checks just one number. Overlapping ranges are handled naturally by marking the same positions multiple times. This solution is efficient since it processes each range and ranges once and checks the target range in linear time. The space complexity is constant, O1, due to the fixed size coverage array, making it suitable for the problem's constraints. This is the Java implementation of the LeetCode problem number 1893. Check if all the integers in a range are covered. The logic mirrors the Python solution, with explicit type declarations and array handling in Java. The solution uses an integer array to mark the coverage status of numbers from 0 to 50, then verifies if all numbers in the target range, left, right, are covered. The approach is efficient and adheres to constraints, leveraging Java's loop structures for range processing. To solve this problem, we start by initializing an array called coverage with a size of 51, filled with zeros. This array will help us track which indices are covered based on the given ranges. Next, we loop through each range in the input ranges. For the range 1, 2, we mark indices 1 and 2 in the coverage array by setting them to 1. Then, for the range 3, 4, we similarly mark indices 3 and 4 as covered. At this point, the coverage array reflects all numbers covered by these two ranges. Adding the range 5, 6 to our coverage array, we mark indices 5 and 6 as covered. Now our coverage array fully represents all the numbers covered by the input ranges. To check if all integers in the target range, left, right, which is 2, 5, are covered, we simply verify that the values at indices 2, 3, 4, and 5 in the coverage array are all 1. Since they are, this means every number in the range 2, 5 is covered, so we return true as the output. For this example, we again start by initializing the coverage array with zeros. Then, we process the first range, 1, 10, marking indices 1 through 10 in the coverage array as covered. Next, we mark the indices from 20 to 30 for the range, 20, 30. Now, we need to check the target range, 11, 15. When we check the value at index 11 in the coverage array, we find that it is 0, meaning the number 11 is not covered. Since not all integers in the target range are covered, we immediately return false as the output. In this edge case, we begin by initializing the coverage array with zeros. The given range, 1, 50, covers all numbers from 1 to 50, so we update the coverage array by marking indices 1 through 50 as covered. Now, we need to verify whether all numbers in the target range, 1, 50, are covered. Since all indices from 1 to 50 in the coverage array are marked as 1, this means every number in the range is covered. Therefore, we determine that the target range is fully covered and return true. The output for this edge case is true, as all integers within the range, 1, 50, are covered by the input range, 1, 50. This demonstrates that the solution effectively handles cases where the target range is entirely covered by a single, large input range. To understand the time complexity of our solution, let's break it into three components. First, the initialization of the coverage array. Here, we create a list of size 51, filled with zeros. Since the array size is fixed and does not depend on the input, this operation is constant in time, or O1. Next, we mark the array for each range in the input. If there are n ranges, and each range can span up to 50 numbers, the inner loop marking these numbers can run at most 50 times per range. This gives a time complexity of O50n for marking all ranges. Finally, we check if all numbers in the target range, left, right, are covered. Since the maximum size of this range is also 50, this operation takes constant time, or O1. By combining these steps, we can analyze the overall time complexity. Now, putting all these pieces together, the total time complexity is the sum of the initialization, range marking, and target range checking. Initialization takes O1, marking ranges takes O50n, and checking the target range takes O1. The dominating term here is O50n, which simplifies to O(n) by ignoring constant factors. Moving on to space complexity, the coverage array is a fixed size of 51 integers, which contributes a constant space overhead of O1. For the input data, the ranges list consists of n pairs of integers, meaning it uses O(n) space. Let's look at any other contributions to space usage. In terms of auxiliary space, the solution does not use any additional data structures besides the coverage array. This means there is no extra space overhead beyond what we've already accounted for. Combining all components, the overall space complexity is the sum of the coverage array, which is O1, and the input data, which is O(n). Therefore, the total space complexity of the solution is O(n). This efficiency in both time and space usage makes the solution well suited for the constraints of the problem. Let's compare this optimized solution to a brute force approach. A naive method would involve iterating through each number in the target range, left, right, and checking whether it falls within any of the ranges in the ranges list. This would involve an outer loop of at most 50 iterations for the target range, and an inner loop that checks all in ranges. The total time complexity for this brute force approach is O(50*n*), which simplifies to O(n). While this has the same asymptotic complexity as our optimized solution, the brute force method is less efficient due to redundant checks. The optimized solution avoids these inefficiencies by pre-computing a coverage array, where all covered numbers are marked in a single pass through the ranges. This significantly reduces constant factors in runtime. Let's consider the best, average, and worst case scenarios for this solution. In the best case, if the ranges list is empty or does not overlap with the target range, left, right, the function quickly completes after initializing and checking the coverage array. This results in a time complexity of O(n) for marking ranges. In the average case, where there is moderate overlap between ranges and left, right, the time complexity remains O(n) because the marking process is efficient. In the worst case, when all ranges in the target range span their maximum sizes, the solution still operates in O(n) time due to the linear marking of the coverage array. The space complexity also remains O(n) across all cases. The efficiency is mathematically guaranteed because marking ranges involves at most O(50n) operations, and checking the target range is constant at O(1). Together, this confirms the overall complexity is O(n) for time and O(n) for space. When tackling this problem, it's important to avoid some common mistakes that can trip you up. One frequent issue is not properly accounting for overlapping ranges. For example, if multiple ranges cover the same number, failing to merge or process these overlaps carefully could lead to redundant checks or incorrect results. Overlapping ranges should be handled in a way that ensures each number is only counted once. Another mistake involves inefficient implementations, such as using nested loops to check if each number in the range, left, right, is covered. This can result in O(n*(m) time complexity, which becomes impractical for large inputs. Instead, aim for more efficient techniques. Lastly, edge cases like an empty list of ranges or a scenario where left is greater than right are often overlooked. Ignoring these can lead to runtime errors or incorrect outputs, so always ensure these cases are handled properly in your solution. Another common pitfall is making assumptions about the order of the input ranges. For instance, assuming the ranges are already sorted can lead to missed or double-counted intervals if this isn't the case. Sorting the ranges explicitly as part of your approach ensures predictable behavior. Additionally, the choice of data structures can significantly impact performance. Using basic data structures like lists for managing ranges may result in slower range queries. Instead, leveraging more efficient structures like sets, prefix sums, or even trees can dramatically reduce time complexity and improve the overall efficiency of your solution. The key is to select the right data structure based on the problem constraints and the size of the input. Now, when approaching this problem in an interview setting, there are a few key insights to keep in mind. First, recognize that this is a variation of interval processing problems, which often benefit from strategies like sorting or using advanced data structures such as segment trees or prefix sums. These tools allow you to optimize the range checking process. Aim for a solution with a time complexity of O(n plus m log m, where m is the number of ranges and n is the length of the interval, left, right. This can typically be achieved through sorting and a single linear pass. It's also crucial to clarify edge cases with the interviewer, such as handling empty input or out-of-bound ranges. Finally, be prepared to discuss trade-offs between different approaches, such as the simplicity of brute force versus the efficiency of sorting or advanced data structures like segment trees. Understanding these trade-offs shows a deeper grasp of problem-solving strategies. Related problems like merge intervals and interval list intersections can serve as great practice to build your intuition for this type of question. Several alternative approaches can help you solve this problem efficiently. One option involves sorting the ranges by their start points and then merging overlapping intervals. This simplifies the process of checking whether all numbers in, left, right, are covered, though the sorting step adds m log m complexity. Another approach is to use a prefix sum array, where you mark coverage for each number in the range. This allows for constant time range queries but may require additional space. A set-based approach is also straightforward: store all covered numbers in a set and then iterate through left, right to verify coverage. While simple, this method can consume significant memory for large ranges. Finally, for dynamic scenarios, you could use a segment tree or binary index tree to efficiently update and query ranges. Although these structures are more complex to implement, they provide optimal performance for frequent updates and queries. Choosing the right approach depends on the problem's constraints and the trade-offs you're willing to make between implementation complexity, time, and space efficiency. Great job! To summarize, we discussed how to check if all integers in a given range are covered by sub-ranges and explored the brute force approach. Remember the key takeaways about analyzing constraints and identifying when optimizations are needed. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!